So it is my privilege to introduce our today's guest, Professor RUPAMANJARI Ghosh. So Professor RUPAMANJARI Ghosh is a researcher, teacher, and orator, and an academic administrator par excellence. She is a former Vice-Chancellor of Shiv Nadar University and a former Professor of Physics and Dean of School of Physical Sciences at Jawaharlal Nehru University, New Delhi. Professor Ghosh has BSc Physics Honors and MSc Physics degrees from the University of Calcutta and a very well recognized PhD from University of Rochester, USA, where she worked as a Rush Fellows. Her research interests are in the experimental and theoretical quantum optics, laser physics, nonlinear optics, and quantum information. Her pioneering work with Professor S. Mandel on two-photon interference has yielded a new direction in the quantum optics and quantum information, in the creation and the use of a source of entangled photon pairs and of a single photons at the forefront of research today. Professor Ghosh has served as a chief advisor for the NCERT science textbooks for the classes 9th and 10th and developed a fresh under National Curriculum Framework 2005. Professor Ghosh joined the newly established Shiv Nadar University in 2012, where she held the position of founding director, School of Natural Sciences, founding dean, graduate studies and research, founding chairperson, gender committee, founding head, faculty development center, founding chairperson, IQAC, that is internal quality assurance cell, etc. And she was also vice chancellor for 2 terms till January 2022, with the full responsibility of functioning the university. Professor Ghosh was felicitated as a visionary education leader of India by Rethink India organization, New Delhi, in December 2017. And she also held several visiting faculty and scientist position on invitation abroad and delivered numerous invited research seminar in India as well as in other countries. Professor Ghosh is a recipient of the Sri Shakti Science Sanman for her original contribution to the science. She received the Department of Atomic Energy, Government of India's C.V. Raman Lecture Award in 2018 and 19. So with this brief introduction, I invite Professor Ghosh to deliver her lecture. Over to you, ma'am.
Thank you so much, Dr. Dongen. And I'll share my presentation, but let me just start by thanking Dr. Shankara Raman for persisting and making sure that I'm with you this evening. It has been really a very good series. The timing in India sort of suits me, but I don't know whether most of you are a little tired, particularly my Indian colleagues who are joining from here. It's 7 p.m. past 7 p.m. But you know, the organizers wanted a talk of general nature rather than focusing on or limiting to my research problems. I am quoting exactly. So I'll definitely follow this instruction, but also highlight my group's research in the process. So it's a big story that I'm going to share with you. And I have named it as Taming Quantum Entanglement, which is the resource that we'll be focusing on. So they're kind of mysterious features of quantum mechanics. And the point for me to start this was the Nobel Prize in Physics this year. As most of you are aware, the Physics Nobel Prize in 2022 went to Alain Aspect, John Clauser, and Anton Zeilinger for experiments, and this is the citation, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So what is this all about? I'm going to give you a flavor of the status today, because most of the work of these scientists that got honored this time were done much earlier, and we are seeing some fantastic results today. So I'm going to take you through that journey shortly. Just to keep it the general, let me take you back to when quantum mechanics got started. We understood that it demanded a whole change of philosophy from classical physics, which had determinism at its core. You know trajectories, if you know initial conditions, and you know the equation of motion, and so on and so forth. From there, we had to move to understanding and accepting quantum mechanical predictability, which can at best be probabilistic, with an intrinsic indeterminacy. It's nothing to do with how inefficient I am, but there is something intrinsic you cannot get out of. And just to bring some life to this discussion, as you all know, Einstein dismissed this uncertainty by saying God does not play dice with the universe. You may wonder what his idea of God was, and I think that he believed in mathematical laws of nature. So maybe his idea of a God was someone who formulated these laws of nature and then left the universe alone to evolve according to these laws, whatever. So this one part was this intrinsic indeterminacy. And the second part that we are going to talk about is really mysterious, is entanglement. And Einstein called it spooky action at a distance. So this entanglement, in very simple words, is what happens to one of the particles in an entangled pair that determines what happens to the other particle, as if one particle effectively knows something about the twin instantaneously, even if they are far apart. So this really was a spooky action at a distance if you have twin particles which are entangled. So for a long time, the question was whether the correlation was because the particles in an entangled pair contained hidden variables. Those are instructions that tell them which result they should give in an experiment. John Bell in 1964 developed a mathematical inequality that sort of brought in a lot of debate in this, and I would not go through the full history, but there are practical experiments done by John Clauser in 1972 onwards that violated a Bell inequality. There are some loopholes. One main one got plugged in by the experiments 10 years later, Alain Aspect did, and he decisively proved that quantum mechanics cannot be replaced by such a hidden variable theory. So this was the debate that Einstein started. So let me take you back to something extremely simple, the double slit interference, and all of you, I'm sure, is familiar with this, that if S is a source, and for simplicity, I assume that it's of one color, and it is a very weak source, is yielding one photon at a time that's traveling from the source to the detector D. In between, there is a screen which has two tiny holes, A and B. Now, if I close one of the holes, B, say, I get the detector to respond, say, 1% of the time. If I close the other hole and open the second hole, B, then assume that it's the same symmetric situation, you get 1% of response at the detector D. When you open both, it's light plus light doesn't give you always more light. It depends on the position of the detector. So opening a second hole does not always increase the amount of light reaching the detector. Sometimes you get more clicks than expected, 1 plus 1, 2%, maximum could be 4%, and sometimes 1 plus 1 gives you 0, no clicks at all. So this is something that we know, and if you read Feynman Lectures in Physics, is volume 3, first chapter, he calls this, that this is has in it the heart of quantum mechanics, the double slit interference. It contains the only mystery. We cannot make the mystery go away by explaining how it works. We'll just tell you how it works. And in telling you how it works, we'll have told you about the basic peculiarities of all quantum mechanics. These peculiarities are the mysteries that I'm going to talk about, but not the double slit interference. But let me go back and tell you what was so peculiar about it. If the source was emitting one photon at a time, then one photon, when it's striking the screen of the detector D, it would give you one tiny dot, one blip. But it has the probability amplitude of going through both A and B. So it was Dirac who said that we should think of this single photon as being associated with both paths simultaneously. Remember what I said about determinism of classical physics to this kind of fuzziness of trajectory. So there are two indistinguishable paths in this case, source through A to detector and source through B to the detector. These probability amplitudes are interfering. If we try to determine with which beam the photon is associated, during the course of that determination, we would force it into one or the other, and no interference would occur. You would get 0 and 2%. So there is no reality really. Earlier, we used to think physics sort of probes the objective reality that already exists. But here, depending on how you are measuring, your reality is changing. And it's also very peculiar that we are going to talk about that there is no locality. There's an extension of the wave function. What if many photons or more than one photon, say two photons, two atoms can be linked in a single wave of light or matter. So this is really is very, very fascinating. And you can ask the question, particularly youngsters, what's the use? And I'm going to touch upon that. The entire lecture is actually based on that. Now, remember that Dirac had said, it's a classic textbook, Principles of Quantum Mechanics, that each photon interferes only with itself. Interference between two different photons never occurs. Now, in my experiments way back, I sort of proved this statement to be false. Now, I have shown two photon interference, but that cannot simply be described in terms of interference of two independent photons, but you must go back to Dirac's interpretation as superposition among indistinguishable two photon paths, two photon amplitudes. So for this peculiar things to see, you have to prepare light in quantum states. Now, those are the peculiarities that I worked extensively on, first from resonance fluorescence from single atoms, and something that I'm going to touch upon today is twin photons from a down converter. So we'll talk about it. So you can have a two photon Fock state, for example. It's then possible to make two photons being emitted by independent sources interfere. There is a theory paper and an experimental paper. It's way back in 1986 and 87. What am I talking about? And these are those two papers. You don't need to go through it right now, but most of you probably know. These are the first papers that talked about two photon interference, and the interpretation, quantum mechanical interpretation of interference that Dirac gave tend to be valid. I'm going to show you a textbook example where this was quoted, but I'm sure you can't quite read what is written. So I have amplified that. In this thin book called The Quantum Challenge, the authors describe that Alain Aspect perfected his source, which was the calcium cascade around 1982 or so. And he went on to use it in important series of experiments that examined the physics of entangled states. So I came much later, around 1985 or so. I started at the University of Rochester through a process known by the intimidating name of spontaneous parametric down conversion. A single ultraviolet photon can fission into two if it is passed through certain crystals. So an UV photon can fission into two IR photons, and the two down-converted photons are in an entangled state, perfectly suited to a whole range of new experiments. And in the book, then they go on to talk about what they are calling the pioneer work of Ghosh and Mandel. So this was 1986 and 87, what I showed you. And he goes on to say just that it's not a new source, but the experiment that I did, it was a new experiment. That's the subject matter. So my work is sort of sandwiched between the Nobel laureates' work, this year's Nobel laureates' work, but the work was done way back in the 80s. So the Ghosh-Mandel experiment is similar to the EPR thought experiment, the Bell's inequality experiments that I just mentioned, in that the two observers must actually compare the data in order to realize that anything interesting is going on. If you look at single photon detection, they are independent, so therefore random. The non-local effect exhibited by the Ghosh-Mandel experiment is quite remarkable, and it's impossible to understand it classically. Now, this is where it all started. This two-photon interference that I'm talking about and the entanglement of these twin photons have been even quoted in popular science book. This book, The Age of Entanglement, for example. Again, you can't quite read what is written, so I'm just elaborating on that. So one day Horn was wandering through Schultz's lab when he saw a recent PRL, that's in 1997 PRL of mine. Thumbing through it, he came upon their double diamond experiment turned from theory to fact by me, working on my PhD with one of the pioneers of quantum optics, Leonard Mandel. Ghosh and Mandel had discovered the entanglement latent when light strikes a crystal in a beautiful process of spontaneous parametric down conversion. This down conversion turned out to be the ideal source to perform the two-particle interferometry experiment that Zeilinger and company has been seeking. So there's an entire description based from the experimental point of view of ZHG, inequalities and so on and so forth. So I think this is how it all started. And it's really quite nice that after all these years in 2022, finally, these pioneers got the Nobel Prize, and it's much delayed but much deserved Nobel Prize this year. So the source of entangled photons sort of looks like this. If you look at the picture on top, this is what I was talking about. This is taken from my paper. And infinitely many pairs meet the phase matching constraints, by which this fission is the most efficient one. So you basically get to see photon pairs emitted along the intersections of the cones, and they're entangled in polarization. A lot of work happened in that direction afterwards. Now, so entanglement, these are all issues of quantum correlations. If you're just working through the mechanics of it, they're nothing surprising really. But if you think about what exactly they're signifying in the physical world, they're absolutely mind-boggling. So when the quantum state of each particle of a group cannot be described independently of the state of the others, including when the particles are separated by a large distance, the fact that they are born together, they carry that correlation through. Now, we have worked on this a number of years later on different schemes and so on and so forth. You may look at that. Now, what's the use of this part? Of course, we found out there are numerous applications of this. You can measure very short time intervals between two photons by a fourth order interferometry, where you don't look at intensity modulation, but you look at intensity correlation modulation. That's a fourth order interferometry. You can, of course, test quantum mechanical non-locality by Bell inequalities. That has been done, and it has been recognized. There are industries that were interested in communication by not a single channel, but two-channel correlated signals, and you would be able to successfully communicate even in the presence of high background noise, because noise will not have this correlation. So and so forth, a lot of applications were thought about. Now, all of this, where are you going with this? This concept of quantum parallelism exhibited by a single photon in the double slit interferometer, that its path could be either through A or through B, and actually together you can't really separate out which way did it go. This can, if it is really true that that's the way nature is working, then can you exploit this to construct a quantum computer? A quantum computer, by now, most all of you probably know, it works on the principle of a quantum bit. That's the basic unit. It's not a binary digit or a bit, but it's a quantum version of it. Instead of zeros and ones, it's a infinite information content in superpositions of zeros and ones. It's like saying maybe rather than saying no and yes, a binary. Rather than having a dead cat or an alive cat, you're basically looking at a mixture of the two, superposition of the two. So if this is really true, then the point is that if you have, for example, a 10-qubit quantum processor, it can process 2 to the power 10, that is 1024 possible inputs at once, rather than doing it sequentially. So how to produce, observe, and make use of such powerful information-rich states is the real challenging question. So the quantum challenge, by that, what we mean is that quantum mechanics shows up, as it was known earlier also, in small enclaves within the classical macro world. The behavior of individual constituents that make up our world, for example, atoms, for matter, or photons, they are described by quantum mechanics. But these particles are rarely isolated. Okay, and as they interact with their what we call environment, they lose their peculiar quantum character. So you no longer see both a dead and an alive cat. You see either dead or alive. You don't see an atom both upstairs and downstairs. You don't see a photon going through or electron going through both A and B, but you actually see them following the classical trajectory. So if you cannot isolate these quantum constituents of our regular world, you don't get to use any of these peculiarities and fascinating aspects of quantum mechanics. So the central question that we have been probing in our group is the mechanism of transition between the quantum and the classical world. Is there a door that you open to go from the classical to the quantum world and vice versa? What is really determining whether you want to treat the system classically and which limit takes you to quantum? Smallness used to be, I'm talking a little loosely, smallness used to be a condition, but we now know it's no longer true. But before I come to the solutions, let me say that what is the other problem? And what is the quantum challenge? Second part. to make a measurement, not only you need to keep a quantum system isolated for long enough, it's a coherence time concept, but also probe it so delicately that the measurement itself leaves the system's quantum nature intact. This was known even to Schrödinger around 1952 or so much earlier, that the single particle detection, he called it post-mortem physics, because by doing this, it's like post-mortem, you're destroying the object under investigation. The moment you detect the single particle, it loses its quantum character. So that was called post-mortem physics by Schrödinger. So observing such fragile quantum effects and then making use of a system's quantum nature are really tough and challenging tasks. Again, why am I talking about it? And this thing has been pointed out very nicely in a review article that you can see. This came out late March this year. Quantum computing has a height problem by Shankar Das Sharma. Essentially, what he's talking about, the main issue in such quantum processors leading to a quantum computer, is that quantum states disappear, or what I would explain, decohere, in the presence of environmental noise, and error corrections are difficult. That's the main issue that Shankar Das Sharma lucidly points out in this end of March article. And the reference is right there. It's, you can actually look it up. So essentially, to have quantum computation, you have to have entanglement of large quantum states to perform efficient calculations. Now, such states will interact with their environment. The nature of the interaction and the time scale over which it acts are critical inputs. So you have this problem of damping and dephasing in quantum systems, and time irreversible outcome of a measurement. The point I'm making is, how well do we understand the process of loss of coherence and emergence of classicality? Only if you understand it, you can probably prevent it when you need to do quantum computation within the time scale in which this coherence is still maintained. Now, I'm not going to go through this in some detail, but these are some basics for you to follow some of the papers that I'm going to refer to. System coupled to its environment, you can actually model it. There are two things that we know, that two effects that happen both for classical and quantum system. One is dissipation, that energy may irreversibly transferred from the system to its environment. The second, associated causally linked, is fluctuation. The fluctuating force exerted by the environment on the system is like Brownian motion that causes fluctuations of the degree of freedom of the system, as in Brownian motion. Now, in quantum domain, there is an additional feature. As the system and the environmental degrees of freedom get entangled, a coherent superposition of quantum states, like we are talking about, 0 plus 1, may be destroyed in a process called decoherence. And I'll give you an example of that. But before I move on to this, I'll not spend much time. What is a very important point for all these real systems is the time scales of evolution of the system plus environment. There are 4 major time scales associated with the problem, and we need to pay attention to that. An example of the decoherence phenomena that I'm talking about, I've taken it from Zurich, famous 1981 paper. Think of the system to be a spin-up, spin-down system. An apparatus is also a detector, which is spin-up, spin-down. So you can write down what is the density matrix of this system. And in the basis where spin-up system, spin-up detector, and spin-down system and spin-down detector, the density matrix has a simple representation. So diagonals are mod A square and mod B square, which tells you what is the probability of finding the system in the up state and in the down state respectively. But the off-diagonal terms that are in blue, they correspond to superpositions of macroscopically distinct outcomes, up and down together, down and up together. So these are classically unacceptable and essentially quantum. As you remember your basic quantum mechanics, it was von Neumann who around 1932, I think, came up with this ad hoc postulate of reduction. This is a non-unitary process that reduces the pure rho to the mixed rho r. There is no dynamics known for it. So you basically set the off-diagonal elements to 0. And from there, the collapse of the classical probability distribution happens. That's not really very interesting. But how did you get these zeros in the off-diagonals? Once you have it, then rho r, the mixed rho, is easily interpretable like classical probabilities. So the dynamics of this is something that my group, we probed in very many systems to understand, because if you believe in quantum dynamics, you do not want to have this non-unitary postulate doing the job for you. So we wanted to look for those dynamics and address the question I just posed: how does classical behavior emerge from quantum dynamics? And a series of papers with many systems, many fundamental systems, we actually continued exploring this problem, and the results are extremely interesting. So that's one very major aspect of decoherence. But in spite of this, there has been spectacular progress in manipulation of quantum states of matter and encoding, transmission, and processing of quantum information. And I go back 10 years when the Nobel Prize in Physics in 2012 were given to Sarge Harosh and Dev Wineland for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So in spite of decoherence, in spite of the quantum challenge that I narrated, these groups were able to measure and manipulate individual single photon kind, single atom kind of individual quantum systems. I show this picture. This is slightly aside. I took it from Sarge Haroshi's Nobel lecture. And in this picture, what you see, 3 generations of Nobel laureate, in which now we have added the 4th one. So the second from left is Claude Cohen-Tanuji, who got the Nobel much later in 1997. This picture was taken in 1966 after Kastler got the Nobel Prize. Kastler is the 3rd from left. Cohen-Tanuji was in the same lab, much younger at that time, but he got the Nobel Prize in 1997. 4th from left is Sarge Harosh, who got the Nobel Prize in 2012. And now Alain Aspect also has the same lab traditions, but of course he has worked in, his recognition came for different systems. But it's really fascinating to see the same lab room in 46 years, 3 Nobel generations of Nobel laureates. There's a lot of work that has been done to talk about optical systems. I'll not get into the details of it for lack of time. But I want to focus on one aspect. In an optical computing system, how do you actually make a memory? And I'll tell you a little bit of fundamentals. Electromagnetically induced transparency is a phenomenon, EIT, as the name suggests. It talks about induced transparency in materials that were actually otherwise opaque because they were on resonant with the light that is trying to go through it. So how do you actually make a material that was opaque to begin with actually in spite of a resonant light and make it transparent? So that's induced transparency is what I'm going to talk about. And this happens by, look at this cartoon. This is a typical 2-level atom. Assume that the 2 levels are separated by h bar omega naught energy or frequency omega naught. And I'm probing it with the red frequency omega, which is delta detuned. A typical absorption and dispersion curve for the frequency omega would be something like this, where in the absorption curve, you will have a peak at delta equal to 0. When on resonance, the light omega would be absorbed, right? That you understand, it will lift the population and it would be absorbed. Causal relationship gives you the dispersion, which has a funny anomalous kind of a look where you actually see this. Now, if I add a 3rd level and shine a little stronger laser on that transition, the transparency or absorption and dispersion profiles get altered very drastically. Where earlier we had an absorption peak, now we have a dip. That means at delta equal to 0, now the resonant light omega is seeing transparency and it would actually pass through. Similarly, the dispersion profile gets altered and now you have a positive slope around delta equal to 0. So, of course, there is a electromagnetically induced transparency that you see within a small frequency window. The light would actually pass through, and there is also extreme positive dispersion in this window that leads to what we call slow light. What is slow light? If you look at the group velocity expression, the way we study in Jackson or other textbooks, you actually write the group velocity inside the material as c, which is the free space speed of light, divided by ng, which is the effective group index. Now, for glass, it would be 1.5, for water, whatever, 1.33, for some semiconductors, it could be 6, 3, whatever. So the group velocity inside the material is always less than the free space speed. Now, that is nothing surprising because also light gets slowed. Here we are talking about very, very slow light. So ng, the denominator, could be 10 to the power 5, 10 to the power 6, 10 to the power 7, making the light go through the material almost like a cycle speed. So how slow can it get? And the question that probably you would be asking, if I'm slowing it down so much, can I actually stop it? Can I stop light inside the material? And I'm going to address that. If you can stop it, then basically you have an idea of how to create a quantum memory. Now, again, what is the physics of EIT? What is the physics of electromagnetically induced transparency? Again, it confronts us with two fundamental quantum ideas. One, that of probabilistic interpretation, and second, addition of probability amplitudes for indistinguishable paths. This is how you can understand the physics of EIT. There are multiple routes of excitation from the lower level B to the upper level A for the probe. So absorption of the probe can happen by two channels. One is a direct one, B to A. The second one would be mediated by the strong laser, B to A to C to A. And these two paths interfere. These two probability amplitudes interfere, and that leads to a cancellation of the probe absorption along from B to A, as the coupling becomes much stronger. The Rabi frequency associated with the coupling is much stronger than the probe Rabi frequency. Now, like in two-photon interference, that double slit we talked about, there is always a coherence lifetime involved. These fragile quantum effects are limited by the coherence lifetime of the lower levels, C and B, and this goes by the name of Raman. It's a Raman coherence time. It's a two-photon coherence time. Till this coherence of rho BC is maintained, you'll see EIT. Rather than this hand-waving argument, you can actually work it out with the dress picture, and I would not get to the details of it. Solve what are the new eigenstates, not ABC, but the new eigenstates of the system, which is now the two light fields plus the three-level atom. And you actually get the dark state that is shown in the red, that in spite of being on resonance, actually doesn't get to see the light. So EIT happens when the dark state is actually the lower level, and when population is stuck there, they actually don't ever go up, even when the incoming probe frequency is resonant to that. The general EIT scheme needs a lambda like this, capital lambda, and the EIT condition is on two-photon resonance when the little delta R, the Raman detuning that's shown on top, is 0. And this is something that we have worked extensively. And what is the physics of it? Sorry, this is a little crowded slide. Photons with 0 rest mass cannot be at rest. Now, can I really stop and restart light? Yes, you can, because light plus matter interaction creates rest photons. For example, in this case, polaritons, which are joint oscillations of light and collective atomic dipoles. Those have non-zero rest mass. The rest photons have non-zero rest mass. So therefore, it can have zero velocity in a moving frame of reference, for example, in a moving medium. There have been other work done in this, and there is a reference given for a PRL in May, though it's not what I'm talking about, but it's an extremely interesting piece of work about self-stopping of light by self-interaction mediated by the resonant nonlinearity. What I'm talking about is that you have the frequency, amplitude, and phase of the incoming light, and you can actually modulate and change those, and you can carry information that are expressed by these modulations of the parameters of frequency, amplitude, and or phase. So when the light stops, that information that was being carried by the light is stored in collective atomic excitation, just like information is stored in the electronic memory of a computer. And to retrieve the information, the control laser is turned on and out it comes. I'm going to show you a bit of cartoon again. So quantum memory essentially for me is a flying qubit going to a stationary qubit, and on demand, the stationary qubit releasing the flying qubit. So this is a cartoon of a storage and retrieval protocol based on EIT, electromagnetically induced transparency. So suppose I have a material in which I have created this perfect lambda, and it has been prepared, all the population is in the lower state B, and I turn on first the control laser, nothing else is happening, then comes the probe pulse. When the probe pulse comes, when it has entered the material completely, I turn off the control laser. So what happens at that point is perfect storage. The state of the light is stored in the Raman coherences, which is the coherence between the two lower ones. And when I want to retrieve it, on-demand retrieval would mean I turn on the control between A and C again, and out comes the probe pulse. So this, I hope you understand that what I am talking about, to control the behavior of an atomic medium to switch between transparency and absorption at multiple frequencies. This has been utilized to create logic gates. And as you realize, the process again relies on on the quantum interference between multiple paths of absorption or emission. So the first trick is to select a simple usable atomic level configuration, which will have that lambda type. And we worked with really bulk quantum mechanics at room temperature, just for demonstration purposes. Worked with helium-4, which has no nuclear spin, I is 0, so therefore there's no hyperfine levels. So it was possible to use sigma polarized light acting on Zeeman sublevels to select a perfect lambda system. Now these were all done in the French collaboration with Fabien Goldfarb and my good friend Fabien Bretneka. And there are two in the French projects which we had excellent outcomes, and that has been highlighted in the newsletter of the Indo-French Center way back. So a series of work, I would not bore you with the details of what's in there, but this is really a lot of work has gone into creating an atomic memory kind of a situation. Some of it you can see, I would skip this. But essentially what am I talking about? I'm talking about photonic channels appropriate for quantum communication over distance because of its fast transmission speed and weak interaction with the environment. Because photons are very fast and they don't really interact with the environment much. But photons are difficult to store, so you can't really use them as memory. They're good for channels. Atoms, on the other hand, could be good for memory because atomic nodes are difficult to transport over distance, but like I showed, they could be good quantum memories. So essentially, a quantum information system will have this atom-photon network, and the major issue here is the information transfer problem. You have to transfer quantum information from the photonic system to the atom without knowing what the information is, right? The moment you know, you measure, you actually destroy the quantumness of it. It becomes classical. So with perfect fidelity, you need to transfer that. We have worked on that quite a bit. I understood how slowly can we turn off or on the control field. When I say turn off, turn on, adiabatically you have to do it, but how slow is slow? What is the impact of spontaneous decay? And we have probed this with model systems. A lot of work has come out in this, but I just wanted to bring you up to date that in room temperature, like we had done it in helium-4, there's a good group that has done it in room temperature cesium cell that has been used to store light onto spin orientation. This paper came out Nature Communication 2018, and the storage times were very long, about 1 second at high atomic density. So it's a remarkable piece of work. And if you want to read the review, this has come out this year again, a lot of hype around this. This is a good Chinese review. In April this year, there is a EIT quantum memory for non-classical states of light. And right after that, there was another Nature Communication in May this year that talks about high performance cavity enhanced quantum memory with warm atomic cell. This was again work done with rubidium. You can take a look at it. I don't have time to go through all the details, but the entire principle that I described is the same thing being carried on. I wanted to talk to you about one peculiar aspect of what I have just shown you. This is not related to the quantum memory problem, but this is something very, very fundamental. If you remember, my expression for the group velocity was C by ng. Ng was the group index. And you can easily make out from this expression that I was talking about slow light when ng is much larger than 1, right? So group velocity Vg would be much less than c. So you can actually go to fast light conditions where ng is less than 1, then Vg could be greater than c. Or you can even have backward light when Vg would be negative when ng is negative. How can ng be less than 1? If you look at the denominator in the expression on top, if the second term in the denominator is negative, easily you would have ng less than 1. So fast light would mean, it's very counterintuitive, but that light is actually, group velocity is going faster than the speed of light in free space. Backward light would mean that the light actually doesn't enter, it comes out before it even entered. So really funny things, if you take this pictorial understanding of group velocity in these extreme cases. But I just wanted to tell you that the superluminal or backward light concepts, these are counterintuitive, but these conditions do not violate Einstein causality, because these waves are actually not carrying any information. Information propagation is better described by discontinuous front velocities. You have to turn on something. And so group velocity is really not responsible for information propagation. So when I was in high school, we all thought nothing could exceed the speed of free space light. Then later in Berkeley experiments, when I was in the US, I learned that, okay, phase velocity, and we understood it perfectly, phase velocity, velocity associated with particular frequency components can exceed the free space speed, but group velocity is the one that's carrying information, and group velocity must be less than c. Now I'm saying that information propagation is not by the group velocity, so textbooks have to be rewritten again. I thought I'll just mention this, don't want to spend too much time on it, but there's perfect understanding of this. The entire truncation of the series, that's the denominator, becomes invalid when you have such discontinuous front velocities. So therefore these expressions lose their meaning. We have done some exploration in this and got really nice results. You can actually not just EIT, you can use something similar, different transmission resonance, similarity ends there, called CPO, coherent population oscillation. This one, there is no atomic coherence involved. A student of mine worked on this as well. We took a double lambda system, a double EIT if you like, which is like a tripod, and went over this nicely and got beautiful applications that this system can be useful as a polarization dependent switch in the presence of a mild magnetic field. So switches, gates, and so on and so forth. There is a EPL on light storage capabilities for intermediate values of detuning that I have not talked about, so I'll skip this for now. And there is a PRL, probably you have seen a few years back in 2017, where we talked about again CPO, this coherent population oscillation, and light storage based on that. Light storage is equivalent to the quantum memory that I have been talking about. So there is tremendous possibility. So having said all these possibilities, I want to tie it down to where are we today? How close are we to realizing the dream of quantum information processing? And there are many jokes, how is your quantum computer prototype coming along? The guy says, great. And he says the project exists in a simultaneous state of being both totally successful and not even started. Anyway, but that's not how it is today. But in real systems, the devices that you see, coming up based on first trapped ions. This is the first qubit in 1995. They're made by Dave Weinlein, Chris Monroe, and colleagues at NIST Boulder. The second kind of devices came with systems of solid-state superconducting circuits. You see by Google, and most famous probably you see the IBM. Till October this year, last month, the IBM Eagle processor, 127 qubit, was the most powerful. Then IBM started scaling up as their plans. So 9th November came on the 433 qubit processor. Then they have very nice plans, and they're moving in the right direction to go for 1,000, 1,400, 4,000 processors in the next few years. Now, this is of course necessary, number of qubits, as I pointed out, that sort of you can do your parallel processing. But this is only one part of a very large and complex puzzle, excuse me, because longer coherence times and reduced noise are as important, if not more. IBM, of course, is scaling up what they call their quantum mainframe, that's Quantum System 2, that will be able to house multiple quantum processors and integrate them into a single system. And this is something that we are looking forward to 2023 end. So these two are were in processor. The reason I want to bring you to this is because of a breakthrough. The atomic quantum processors that came out in April this year. So the first quantum processors that use neutral atoms as qubits, they're produced independently by two groups, one in Harvard, Lukin, and Safman of University of Wisconsin-Madison. Two different systems, first one rubidium, second one cesium. They came out in back-to-back in Nature on the 20th April issue. It's a milestone, it's a breakthrough, because atomic quantum computers may be easier to scale up than the two earlier technologies. Because neutral atoms, as they're neutral, the interaction with the environment, actually would be much reduced and almost negligible. Typical setup looks this messy. This is from Madison, multi-qubit entanglement and algorithms on a programmable neutral atom quantum computer. A lot of work needs to be done. Simultaneously, there's a qubit teleportation. There's a lot of progress in that. Probably have seen this Nature paper that came out end of May this year. Qubit teleportation between non-neighboring nodes in a quantum network. A future quantum network powered by quantum teleportation could provide a new kind of encryption that is theoretically unbreakable. So we are looking forward to all of this, and the resource they all use is really the entanglement that I talked about. So where are we going with this? There's a lot of talk on hybrid computing. What's the right combination of pure quantum, quantum-inspired, and classical computing? Because it doesn't have to be really pure anything, but hybrid computing may be faster coming to the market. There's a lot of work going on photonic neuromorphic computing, this to mimic neurons and synapses emulating the human brain. There's a lot of work going on, not well understood, but this is to boost the prevalent computing capabilities. I'll not touch upon this at all. So to conclude, Einstein used phrases such as God plays dice is something that I cannot believe for a single moment. And he said, the Lord is subtle but not malicious. On one occasion, Bohr answered Einstein, stop telling God what to do. And I think this is what we are trying to figure it out, God or no God, whatever you mean, exactly how things are happening and how we can actually make use of it. Moral of the story for today is that evolution of physics happens when theory and experiment go hand in hand. And quantum computer is an example of that. Whichever way it goes, it would prove a lot of theoretical stuff along the way with the experiments. And fruitful applications do come out of this, and scientific methods continue. It will not be probably in the near future that we have discovered everything and all scientists would become jobless because there's nothing more to do. We'll keep on pushing the frontier of knowledge, and the methodology that is scientific is so important that would continue is what I strongly believe in. So I'll stop here for today, and thank you very much for your attention.